Today, we are going to talk about viscosity. Viscosity is a property of a fluid to resist to flow. Different types of fluids have different viscosity values. It is related to ease with which molecules can move past each other. Viscosity is a function of temperature and pressure. Although the viscosities of both liquids and gases change with temperature and pressure, they affect viscosity in a different manner. It increases with stronger intermolecular forces caused by the increase in the molecular weight and decreases with higher temperature. In determining the viscosity of fluids, the following methods are possible: flow through the capillary tubes, fall of solid spheres through fluids, torque or viscous drag on a rotating disc or cylinder immersed in the fluid, and flow of fluids in an aperture plate. The first enumerated will be the method used in this experiment. A capillary viscometer or an Oswald viscometer consists of two reservoir bulbs and a capillary tube. It will be filled with liquid until the liquid reaches the upper mark with the aid of a pipette to accurately measure out the volume of needed liquid. The objective of this investigation is to determine the viscosity value of numerous types of chemical compounds and the effect of varying concentrations and temperatures to the viscosity value of a fluid.
As mentioned in the introduction, the capillary-flow method will be used in this experiment. But before going into the details, let us first go into the preparation of the samples. Samples were prepared by placing 10 ml of each solution in a regular test tube. Samples were not further purified in the duration of the experiment. Samples to be tested are ethylene glycol, ethanol, and sodium chloride. Ethylene glycol is odorless and colorless. It is a toxic compound, and so ingestion of this must be avoided. This is why wearing your personal protective equipment or PPE is a must. Ethanol is a volatile, colorless liquid that is toxic when ingested in large amounts. Despite being colorless, 1-butanol can be distinguished by its pungent alcoholic odor. Sodium chloride is characterized by its clear, crystalline appearance when processed. Distilled water was also used in this experimentation.
Hi, so this is a viscometer. So I'm gonna show you the parts of a viscometer. This is a reservoir, capillary arm, lower mark, this one, and the upper mark.
Prior to the actual experiment, the viscometer must be calibrated by using a fluid of known density and viscosity as the reference. Doing this calibration will help in the computations involved for this experiment. The calibration of the viscometers is performed by measuring the flow time of the fluid for each viscometer whose value is equal to the standard calibrated flow time. To begin the calibration, the viscometer is filled with tap water until the sample has reached well above half of the fluid reservoir. We suggest using a reference temperature that falls under the 5 degrees Celsius increments. This will save the researchers from the effort of inaccurately interpolating known data, since most comparable literature values are often in these increments. Fluid is then vacuumed up the capillary past both the lower and upper mark using a suction bulb. Once past the upper mark, the bulb was removed and the fluid was allowed to run past the upper and lower mark, during which the researchers must record the time it takes for the fluid to complete its run. Once the calibration is finished, the researcher can now proceed with the actual experimentations. The experiment is divided into 3 parts, with all the parts revolving around investigating the dynamic viscosities of several samples based on the researcher's preferred reference temperature. All 3 parts of the experiment followed a similar process as in that of the calibration of the viscometer, and a total of 2 trials were done for each sample. The first part of the experiment involved determining the effect of intermolecular forces on viscosity. Here, the viscosities of water, ethanol, ethylene glycol, and 1-butanol were computed. The second part involved identifying the effect of changing concentrations of solutions. This portion involved preparing varying concentrations of sodium chloride solutions. The third and final part involved determining the effect of increasing temperature of solutions against viscosity. This portion used water at different temperatures as the test sample.
Fluid flow in different equations. The Boas-Weiss law is used.
The Ostwald-Fensky method makes use of the Hagen-Poiseuille equation in determining viscosities of fluids. The Poiseuille's law states that the flow of liquid depends on following factors such as pressure gradient, the length of the tube of radius, and the viscosity of the fluid along with relationship among them. The equation is: we equate equation 1 and equation 2 to come up with the equation that will be used later. In the equation, V defines the total volume of the test liquid, R is the radius, T entails the time in which the liquid flows, L stands for the length, E is the pressure, and U is the dynamic viscosity. Further rearranging the equation and treating some values as one constant with simplifying conventions, the result would then be: this is the equation that we will be working with, where ρ denotes the density of the liquid sample and T denotes the average flow time per liquid sample.
The determination of the value of V was completed using the dynamic viscosity and density of a known fluid, in this case water, from existing literature with respect to the base temperature. Once computed, the value of A can be utilized to experimentally determine the dynamic viscosities of pure samples, as well as the effect of temperature and concentrations on viscosity.
It is known that the tighter the molecules are made, the more resistive it is to deformation.
From the samples, ethylene glycol is the most viscous, for it has two ends capable of hydrogen bonding. Hydrocarbons with a longer carbon chain exhibits higher viscosity than the ones with shorter carbon chains. High viscosity in this case is influenced by greater surface area. As predicted, 1-butanol has the greater viscosity value compared to ethanol. Water is the least viscous, for it exhibits short molecule chains.
Larger intermolecular forces and greater surface area mean a more viscous fluid.
The effect of varying concentration of a solution to the dynamic viscosity was investigated. Given in the Hagen-Poiseuille equation, the dynamic viscosity is affected by the calibration constant, density of the sample, and the flow time measured. The density of a solution increases with concentration, thus making the sample resistant to fluid flow. Moreover, the increase in concentration decreases the spaces between the molecules, and hence increasing the hindrance to the movements of the latter and giving a more viscous fluid. The effect of temperature changes in a liquid to the dynamic viscosity was examined. The impact of increasing the temperature in a liquid is to reduce the cohesive forces while simultaneously increasing the rate of molecular interchange.
Liquids show a decrease in viscosity with increasing temperature. If your results validated the principles aforementioned, then you did a good job.
The experiment is not immune to errors. Oswald-Pinsky viscometers can cause significant errors in viscosity measurement if the apparatus is not vertically aligned. Another possible source of error is the requirement to use exact volumes of the samples. The challenging part takes place when heated samples are to be tested. Knowing the substance's density in different temperatures will be of great help in adjusting the volume needed.